So more function work for us. Today we're going to talk about combining functions. So we have dealt with what the function graphs look like, what our parent functions look like. Now, can we combine two or more functions to come up with a whole new and different function? First, we'll talk about just simple mathematic operations on functions. We can add them, subtract them, multiply them, and divide them. The one thing that I want us to pay attention to is what happens to the domains of those changed or new functions. Let's say we are given a function f of x and we have another function g of x. We can add those functions, and this is what the notation would look like, by simply taking the entire function rule for f and adding to it the entire function rule for g. What this does is it combines the domain of those functions as an intersection of both of those. Let's say f of x was x squared, and let's say g of x was 1 over x. Well, the domain of x squared is all real numbers, no problem. But the domain of g of x, we have to kick out 0, right? We're not going to have any output values for an input value of 0. So that's why it's not the union, it's the intersection. It's where those two overlap. And so the domain for the sum of this function, the sum of these two functions, would actually be the domain of the limiting function. So we're limiting the domain because we have to kick 0 out of this piece. So that winds up the domain for the sum of those two. And we follow along quickly here, the same for the difference and the same for the product. Those domains wind up being the intersection. If either one of those domains has something missing that the other one actually has in it, the smaller of those domains, the most limiting one, is going to actually be the domain. So these operations are fairly straightforward. We have the same kind of idea with the quotient or with dividing functions, except that we have to make sure that the outputs on the function that's in the denominator do not equal 0. So we have to work with this domain a little bit more than just worrying about the intersection, because this may be a well-defined function, like for instance g of x in this case might be x cubed. Well, that's a well-defined function, no problem, but as soon as I put it in the denominator of a fraction, then I do have to limit the domain because x can't equal 0, because if it did, then the whole function g of x would equal 0. So adding, subtracting, multiplying, dividing, not an issue. Everything pretty straightforward. Given f of x is 1 over x minus 2 and g of x is the square root of x, we can add those functions together by just taking the two separate functions and adding them. The domain of this function is going to have an issue when x equals 2. We've got to kick 2 out of the domain because this function is more limiting than this one. So this one will have to kick out all negative input values. So this is just all positive numbers. This is all positive numbers but 2. So if that makes sense. Here's the difference of those functions, domain the same. The difference of these functions and the domain's the same. But here on the quotient, we're going to get in trouble with the square root of 0. So here 0 is included in these domains, but we have to kick it out of that final domain. So now let's talk about combining functions. Well, here we've just taken x and substituted in 4. So we can evaluate those operations on functions as well at any given real number value. So composing functions. We're going to consider a way of combining functions that's not just adding, subtracting, multiplying, and dividing. Here we're actually going to feed one function into another function. If I have a function f of x that is the square root of x, and I have a function g of x that is x squared plus 1, when I feed g of x into the f of x function machine, in other words, now my input is not just one single domain value, it's a complete other function, g of x, then I'm going to get the composed function or composition of those two functions. And then we do definitely have to pay attention to what happens to the domain values there on the new function. So we take the function rule for f, which is the square root of x, and we take the function rule for g, which is, what was it? It was x squared plus 1. And we're going to feed g into the f function machine. And this is going to result in a whole new function. We're going to call the new function h of x. So we have an h of x function machine that takes whatever I feed it, which is the function f, and then I feed the function f the function g. So there is h of x. So in other words, if we have an input value from the domain of g, and we put it into the g function machine, and it does whatever the function rule defines, which is x squared plus 1, then we take that range. It's not a range value, it's a range expression. That's the output of the function, and put it into the f function machine. Then it's going to do whatever operation f does on its input values, which is take the square root of it. So this is what a composed function would look like. So the composed function is just taking one function and feeding it into another. So make sure you understand this composition notation as well. Sometimes it's just f little open hole g, and that means that I put g inside the f function machine and the domain value is x. I prefer this because I like the whole inside function, outside function thing, but you do need to recognize this notation because you will see it. All right, so here we have the composition again of this function. We take an x, put it into the g function machine. We put the g of x function into the f function machine. So we have a composed function. So here specifically, let's let f of x be x squared, and let's let g of x be x minus 3. So we want f of g of x, which again, I like to write like this, and it says that I take the f function, which is taking whatever I feed it and squaring it, and I feed it the g function. So there is f of g of x, and g of f of x, because I could compose them in the opposite direction, I could take the f function and put it in the g function machine. Oh, sorry, g of f of x, right? And then what I'm going to do is I'm going to take that and I'm going to take whatever I feed it input value and subtract 3. And here the input value is the function f of x. So there are the composed functions f of g of x and g of f of x. It is possible to compose more than two functions. Here it says put h of x inside the g function machine, take that result and put it inside the f function machine. So that's definitely something that can be done as well. So if I want f of g of h of x, then I'm going to start with h of x, put it inside the g function machine, which is x plus 3 raised to the power of 10. And then I'm going to take that and put it into the f function machine. And f of x, just for clarity, is x over x plus 1. So this is what I'm putting into that machine. Everywhere this one has an x, the f of g of h of x is going to have the above expression. So it looks like x plus 3 to the 10th in the numerator over x plus 3 to the 10th plus 1 in the denominator. So we can compose as many functions as they would like for us to. It's not going to be a problem for us. So given big F of x is the fourth root of x plus 9, we need to find the two functions that were composed to give us big F of x. So this says that what's happening over there is f of g of x. So what was put inside? What is the inside function? So g of x would have to be x plus 9, and f of x would have to be the outside operation, which is the fourth root of x. Okay, so composing functions, not a big problem. So come to class next time and we'll work on this for homework.